right, well, good afternoon, everyone, and welcome to space. Today, we're going to hear about NASA's recently launched James Webb Space Telescope, or the JWST, which is the successor to the Hubble. And pardon me a moment, I just had to change my screen here. And we're hearing today about the JWST from Dr. Matthew Greenhouse, who currently serves as Senior Staff Project Scientist for the Webb Science Instrument Payload. He specializes in infrared imaging spectroscopy, development of related instrumentation and technologies, flight project science, and technical management. Dr. Greenhouse earned his bachelor's degree in geoscience from the University of Arizona and Ph.D. in physics from the University of Wyoming. He also holds certificates in both public leadership and policy strategy from the Brookings Institute. Dr. Greenhouse first began work in infrared astronomy in 1979 when he joined the Stewart Observatory as an instrument tech for balloon-borne and Kuiper airborne observatory science instrument development. In 1983, he joined the Wyoming Infrared Observatory as a graduate student in physics, and after receiving his PhD, joined the Smithsonian in DC as a federal civil service astrophysicist. He then joined the NASA Goddard Space Flight Center during 1996 in the same capacity. Dr. Greenhouse has served on several NASA and European Space Agency flight mission teams, and he supported the NASA Spitzer mission by serving on its community task force as Legacy Science Program Chair and the Hubble Space Telescope Wide Field Camera 3 Instrument Project by serving on numerous Gateway technical review boards. Dr. Greenhouse has been a member of the NASA Astrophysics Working Group and has supported ground-based astronomy through membership on the National Science Foundation Committee of Visitors and numerous selection committees and review boards for major ground-based instrumentation. Dr. Greenhouse is the recipient of more than 20 performance awards and honors, including the NASA Exceptional Achievement Medal and the Robert H. Goddard Award for Exceptional Achievement in Science, and he is author of more than 100 publications. So please help me welcome Dr. Matthew Greenhouse, who's going to tell us all about the James Webb Space Telescope, from its conception and its mission to hopefully some of the current data being gathered. So welcome, Dr. Greenhouse.
Thank you very much, and thank you for all of that. Everyone should see a chart on the screen. Is that correct?
Yes. Okay,
great. All right, well, thank you everyone for tuning in to hear about the James Webb Space Telescope. Traveling back in time is the stuff of science fiction, but looking back in time is something that we can actually do. And this is one of the primary applications of space telescopes, is to look back in time. So how do we look back in time? It works as a result of the finite speed of light. If you look at someone who might be seated in the room with you right now, you're not seeing them as they are. You're seeing them as they were a few nanoseconds ago, because that's how long it takes light to travel 1 meter. Now, a nanosecond is a really imperceptible transmission delay, so we don't notice that at all in our everyday lives. But imagine that we had a magic switch that could turn off the sun, and we flip that switch. It would be 500 seconds before we knew that anything happened. That's because it takes light 500 seconds to travel from the sun to the Earth. So when we look at the sun, we're not seeing the sun as it is, we're seeing it as it was 500 seconds ago. Similarly, if we look at the nearest star, we're seeing it as it was 4 years ago. If we look at the center of our galaxy, we're seeing it as it was 25,000 years ago, and so forth. As we look at objects farther and farther away, we are literally looking back in time to see them as they were when the light from them began traveling to us. All right, so what are we going to look back in time to see with the James Webb Space Telescope? The Webb, as we call it, was conceived as a mission in the early 1990s to connect the dots, if you will, between this famous image in the upper left that was taken with NASA's COBE satellite. That is an image of the point in the history of the universe shown on this cartoon when the universe was only a few 100,000 years old. And at that point in time, the universe became transparent and light could escape, and light that we can see. And in this COBE image, these colored blobs that you see are temperature inhomogeneities that are the seeds from which galaxies will eventually form. Now, around the same time, the Hubble Space Telescope had been launched, and Hubble can see back in time to a point where the universe is about 1 billion years old. And Hubble took a famous image that pushed that system to its limits to look back as far back in time as it could to this billion-year-old universe epoch. Now, between the epoch that COBE observed and the epoch that HST could observe, there is a poorly studied, mysterious epoch known as the cosmic dark zone. And it is of great scientific interest because this is the point in the evolution of the universe when the first stars and galaxies formed. And it's mysterious because we haven't had the right type of telescope in space to observe that epoch, to look back in time to this epoch. And that was the original impetus for the JWST mission. And as we'll discuss, JWST does that in lots of other science. Now, when Hubble took that famous image, I don't know why this is jerking, it stared at a specific spot in the sky for a long, long, long time, leaving the camera shutter open, if you will. And this is the image that was seen. It's called the Hubble Deep Field. In nearly everything that you see in this image is a galaxy. And the fact that we have all these galaxies still in the image is telling us that we haven't seen back in time to the galaxy formation epoch. Now, when the Webb repeats this experiment, it will do it much the same way. The Webb will stare at a spot in the sky for a long, long, long time. And however, the Webb has special features built into it that allow it to see farther back in time than the Hubble can see. So when the Webb does this experiment, we expect to see all that there is in terms of galaxies and stars. So there would be nothing left to see. Now, when we say that the Webb will see the first galaxies, we don't mean that you will pick up a copy of the newspaper and see a picture of the first galaxy. Rather, what we mean is that the Webb will study the rate of star formation per unit volume in the universe as a function of look-back time, as a function of redshift. This plot shows what we know today. And one can see that as we get to the high redshift area of this chart, the long look-back time area of the chart, the data develop big error bars and the data stop. And that is speaking to the need for the JWST. So the JWST will fill in this high redshift portion of this plot with high quality data. And we should see a precipitous drop off at some point, which will indicate that we've reached the formation epoch. And the data should be of such a quality that we can distinguish between various theoretical models of how the universe formed and evolved. Now, in the lower left, we have a supercomputer simulation of the evolution of the universe. The normal matter in the universe is distributed in a spider web type arrangement that is shown here. It's called the cosmic web. And as the JWST looks back in time, we will be able to see how this structure formed and evolved over cosmic time. When we look at galaxies with the Hubble, say in the nearby universe, they have the morphologies or shapes that you've all seen in textbooks and posters and so forth. Some of them have spiral arms, some of them have bulges, but they're very symmetric objects, very symmetric morphologies. When we look back in time as far as Hubble can look, we find that the galaxies actually look different. Instead of exhibiting those beautiful symmetric morphologies, they appear to be very irregular and beaten up sort of blobs of light. And the Webb will help us understand how this evolution in morphology of galaxies formed and what caused that to form and what controls it. We do see with Hubble irregular morphology galaxies nearby us today. And we can actually reproduce some of those morphologies and by modeling them as resulting from collisions between galaxies. This computer simulation of colliding galaxies, each point of light is a star. And with simulations like this, we've been able to reproduce those irregular morphologies that we see in the nearby universe. And we believe that collisions like this were more common in the early universe, and that perhaps is the controlling factor. The JWST will help us study this phenomenon. Now, you've all heard the statement that space is expanding. What do we mean by that? This analogy tries to explain that. This is a loaf of raisin bread dough that's been set out to rise. Now imagine that you are seated on one of the raisins. What would you see? You would see every other raisin moving away from you, even though you're not at the center of the expansion. And no matter what raisin you chose to sit on, you would see exactly the same thing. This is a pretty good analogy for what we see in the universe around us. So when we say space is expanding, like this raisin bread dough, we mean that the actual space is expanding. We don't mean that the galaxies are flying through space as if they resulted from a collision, but rather the space itself is expanding. So what does this have to do with JWST? Well, if we want to observe those first galaxies to form in the cosmic dark zone, they emit their light in the ultraviolet part of the spectrum. But as that light travels to us through the expanding space, through that expanding raisin bread dough, its wavelength is stretched from the ultraviolet into the infrared part of the spectrum. So in order to see that light today, we have to use an infrared telescope. We have to observe in the infrared part of the spectrum. And that infrared capability, which is crucial to seeing the first galaxies, it also enables a wide range of other science investigations that the JWST will pursue. So light comes in an infinite spectrum of wavelengths, from infinitely short to infinitely long. But it's all light. And the Hubble Space Telescope was designed to observe from the near edge of the infrared into the ultraviolet. Our eyes can't see the ultraviolet light, but your skin could be burned by it if you stay at the beach too long. Our eyes can only sense a narrow slice of this infinite spectrum of wavelengths. That narrow slice corresponds to a transmission window in the Earth's atmosphere, so this light can actually reach the ground, and our eyes have evolved to be sensitive to it. But there's a lot more light outside that band that our eyes cannot see, and that's very important for science. The Webb telescope, in contrast to Hubble, will observe from the red edge of the visible out into the mid-infrared spectrum. Our eyes can't see that light, but your skin can feel that light. If you hold your hand near an electric stove burner or a radiator and you feel the heat on your hand, what's actually happening is your skin is sensing the infrared light that's being produced by the warm object. So infrared light is heat radiation, and we'll be using that in a lot of science applications on the web. This is a picture of the Eagle Nebula taken with the Hubble Space Telescope. And the spaces between the stars in our own galaxy, the so-called interstellar space in our galaxy and others, is not an empty vacuum. It's filled with giant clouds of molecular gas and dust. And this picture of the Eagle Nebula is a picture of such a giant molecular cloud. Some stars have been born in this cloud, and the UV light from those stars is ionizing the hydrogen gas in the cloud, which is causing this visible nebulosity. Hubble recently, not recently, but early in its mission, took a very famous image of a portion of this cloud in the Eagle Nebula, shown here. And these giant pillars that you can see are pillars of molecular gas that have dust mixed in with them, which is making the pillars opaque. However, when we observe that same field in the infrared, the longer wavelength infrared light can penetrate the dust and allow us to see what's going on inside the cloud, giving us a better view of star formation that is occurring in the cloud. And so JWST will use its infrared capability to study star formation in our galaxies and others. We know the basics of star formation. These giant clouds of molecular gas collapse onto themselves by self-gravity. And when that happens, the pressure inside the cloud goes way up. And so the temperature inside the cloud goes way up. And it can reach very high temperatures where nuclear fusion can occur. And that's how the star is produced. And once the star is formed, it is typically surrounded by a disk of material, so-called circumstellar disk, that one can think of as material left over from the star formation. And these circumstellar disks are of tremendous scientific interest because these are the birthplaces of planetary systems like our own. And when planets form in these disks, the planets sweep up gas and material in the disk to cause the disk to take on this sculpted appearance. Here you have a computer simulation of planets that are orbiting inside a circumstellar disk, causing it to take on this banded, sculpted appearance. And up here in the upper right, we have actual images of these sculpted disks taken with a giant radio telescope in Chile. And so by observing the sculpted nature of these disks, we can actually infer the presence of planets without having to see the planets individually. And JWST will be doing a lot of work on circumstellar disks to understand how planetary systems like our own form. Here in the upper left, you have an artist's rendition of the debris disk surrounding our solar system, alongside a map of where that debris actually is. These icy chunks of ice and rock are of great interest because they are primordial material left over from the formation of our solar system. So we want to study that material. And these are the so-called trans-Newtonian objects, or Kuiper belt objects, that we've known about for a long time, but they're largely unexplored. Recently, we took our first image of a Kuiper belt object, and this is what we saw. We sent NASA's New Horizons mission, which was a mission to go off and fly by Pluto. After it finished with Pluto, we sent it on to take this first image of a Kuiper belt object. And it turned out to be two objects that were fused together. And computer simulations have shown that objects can fuse like this as a result of a very low velocity collision. A single-digit meter per second collision has shown that objects can fuse without either one being destroyed by the interaction. And this is of great interest for theories of planet formation, in which planets form by successive agglomeration of small particles into successively larger ones to eventually form a planet over 100 million years or so. So we put special tracking capability into the JWST to allow it to study the outer planets of our solar system and these Kuiper belt objects. Now, JWST will do work on the planets of our solar system in addition to everything else. The Webb will study Jupiter's Great Red Spot. As many of you know, this red spot is a storm that has raged on Jupiter for more than 400 years. Today, we see that it's shrinking, and the Webb may help us understand why it's shrinking. And the Webb may also help us understand why it's red. We still don't know why the red spot is red. The Webb will search for small moons of Saturn that are too faint for a flyby spacecraft to have seen. But the Webb will also do some of its most interesting work on moons of Jupiter and Saturn, big ones, Europa and Enceladus. Today, we know that liquid water in our solar system is not limited to the Earth. And in fact, it's possible that most of the liquid water in the solar system is not on the Earth. We believe that Europa and Enceladus contain vast oceans of water that are covered by a thick crust of ice. And this, as tidal forces act on this ice, it cracks, it causing a geyser-like phenomena where water vapor is ejected through cracks in the ice. And in the lower right here is an actual image of this phenomena taken with the Cassini spacecraft on Enceladus. So JWST will do spectroscopy on this ejecta to help us better understand its chemical composition. It's possible that life could exist in these oceans. We know that from studies of the mid-Atlantic ridge on the Earth, that life can exist with no energy input from the sun, and the same thing could be happening in these oceans. So it's of great interest to study this ejecta. Now, today we know that for all practical purposes, all stars have planets, and 5,000 exoplanets have been discovered to date. Exoplanets meaning planets that are observing stars other than the sun. And we have learned how to search for life on them by studying their atmospheres. We know that there must be tens of billions of habitable worlds in our galaxy just from the 5,000 planets that we have discovered so far. We don't know that they're inhabited, but the search for extraterrestrial life is no longer the stuff of science fiction. It is very much a major science objective of NASA. So how do we do it? How can we search for life on an exoplanet that we can barely see? We do it with a technique called spectroscopy, in which we spread light out into its component colors to such an extent that we can see the individual emission and absorption of light by atoms and molecules. And with that, we can actually measure the chemistry of the gas that we're observing. So here we have a spectrum of Mars, Earth, and Venus. So what is a spectrum? It's a plot of brightness versus wavelength. And so take the Earth as an example. If the Earth had no atmosphere, this spectrum would just be a flat line. But because it has an atmosphere, this line has all kinds of bumps and wiggles in it. And all those bumps and wiggles are due to emission and absorption of light by atoms and molecules in the atmosphere of the Earth. And we can even identify which atom and molecules is producing each of the bumps and wiggles. So with spectroscopy, we can measure the chemistry of the atmosphere of exoplanets. And we'll be looking for chemical species that are indicative of life. So how do we do it? On the web, we'll be using a technique called transit spectroscopy, in which we'll be observing edge-on solar systems, as shown in this cartoon. Imagine a solar system that we're observing edge-on, so the planets are orbiting along our line of sight, and we have a star, we have a planet, and we have our telescope over here. And imagine that we take a spectrum in this configuration. What are we getting a spectrum of? Well, we're getting a spectrum of the star plus the spectrum of the planet's atmosphere. Now we just wait a while for the planet to move out of the way, and we take the spectrum again. So then we have just a spectrum of the star by itself. We subtract the two, and voila, we have the spectrum of the planet's atmosphere. And this has been developed into an exact science using the Hubble's telescope and others. And Webb will be doing a great deal of this kind of work. The Webb will be studying planets that are typically much larger than the Earth, but the Webb can detect water vapor on an exoplanet that is just a few times the size of the Earth. Why do we care about water vapor? Well, it's not because alien life might get thirsty and need something to drink, but rather in order for the organic chemistry of life to occur on a planetary scale, one needs to have a liquid solvent available on a planetary scale. And water is what we're most familiar with. Now, when we first put pencil to paper or marker to whiteboard on what kind of observatory we had to build to do all of that science, we realized that we needed 7 times the light gathering capacity of the Hubble Space Telescope to see those first stars and galaxies. And we also needed Hubble's ability to see fine detail, angular resolution, as we call it. And we needed that in the infrared part of the spectrum. So here we show this is an image of a certain field in the sky taken with NASA's Spitzer mission, which was our prior infrared mission prior to the Hubble, prior to the JWST. And this is what Spitzer would see on this particular star field in about 25 hours of exposure. And alongside that is a simulation of what JWST would see in just 1,000 seconds on this exact same field. And so you can see immediately the importance of angular resolution. JWST will give humanity its first high-definition view of the infrared universe. Now, when we realized that we needed these 3 things, we then realized we had 2 huge problems that almost stopped the project dead in its tracks. In order to have 7 times the light gathering capacity of the Hubble, we needed a primary mirror that is larger in diameter than any available rocket fairing. And then in order to build an infrared telescope, we realized that we had to make the telescope very, very cold, about 40 degrees above absolute zero, or nearly minus 400 Fahrenheit. And then and now, there is no mechanical refrigerator powerful enough to cool something as large as the Webb to such an enormously low temperature. So those were our 2 problems, and we did solve those problems. Let's take a look at how we did it. First, let's talk about that cooling problem. The Webb was not placed in orbit about the Earth the way the Hubble Space Telescope is. Rather, we placed it in orbit about a special spot in space called the second Lagrange point of the Sun-Earth system. That's a mouthful. We just call it the L2 point for short. And so what's special about this L2 point, and how does that help us cool the telescope? Well, as the Earth orbits the Sun, this pattern of Lagrange points orbit with the Earth, of course. And so if an object is placed at the L2 point, all the sources of heat on that object, the Sun, the Earth, and the Moon, will always lie in the same direction. And so we realized that if we deployed a giant Sunshield such that the Webb telescope could always live in the shadow of the Sunshield, then it would cool passively to the cold darkness of space and reach the desired temperature. But at the same time, we need a telescope that can point all over the sky. And so we sized this Sunshield so that the Webb could tilt 5 degrees toward the Sun and 45 degrees away from the Sun and still be in the shadow. And you can tell intuitively that if we rotate the Webb about the Earth-Sun line, this horizontal line, that doesn't spoil our shadow situation at all. And so now this arc becomes an annulus, which covers about 35% of the sky. So at any moment in time, the Webb can point at 35% of the sky and still be in the shadow of its Sunshield. Now, as the Earth orbits the Sun, we're rotating about this axis. And so one can see that this annulus will sweep over the whole sky every 6 months. So every 6 months, JWST can observe any spot in the sky while remaining in the shadow of its Sunshield. So that's how we solve the cooling problem. Now, we don't put the Webb exactly at the L2 point, but it's in a little orbit about the L2 point shown here. And the reason we did that is we have to stay outside of the Earth's shadow. We're generating electricity with solar arrays. It takes about 2 kilowatts of power to run the Webb. And so we have to stay outside of the shadow. And so we're in this small orbit about the L2 point. That orbit is unstable in the direction of the Earth-Sun line, so it has to be maintained with station-keeping thrusters. And the propellant for that is forecast to last about 20 years. So it's unlikely that that propellant would be the life-limiting item on the JWST. Okay, how did we solve the big mirror problem? We did that by adopting something called a segmented mirror architecture. Instead of building a single giant mirror, we constructed a mirror out of 18 hexagonal segments that are mechanized to play together as if they were each part of a single mirror. And that allows us to fold up the mirror inside of the rocket fairing. We're using a 5-meter diameter rocket fairing on a French rocket called the Ariane 5. And the Ariane 5 is launched from French Guiana, Kourou Launch Center on the east coast of South America. The whole Webb payload is about 6.5 metric tons. In the origami by which this unfolds, that you'll see in the next slide, involves 40 deployable structures and 178 release mechanisms, all of which worked perfectly. So the first thing that happens is the solar array is deployed so that we can become power positive. We're operating on batteries up to this moment. And then the high gain antenna will deploy, there it goes, so that we can begin communicating with the JWST. There are various rocket firings and pitch maneuvers that get us on course to the L2 point. And here you see these giant pallet structures deploying. They have that tennis court sized Sunshield folded up inside them. You're seeing a deployable mast extend here to provide thermal isolation between what will be a cryogenic telescope and what must remain a room temperature spacecraft. And now these telescoping mid-booms pull the 5-layer sunshade out of those palette structures. And these spreader bars on the periphery separate the 5 layers into their special tension shape. A trim tab deploys there to help us balance the solar pressure on the Sunshield. And various other smaller radiators deploy to cool specific pieces of equipment on the observatory. And soon you'll see that there goes the telescope secondary mirror deploying. And now you see the wings of the primary mirror deploy, much like a round drop leaf kitchen table. And all of that worked perfectly after launch. Now, the Webb mirrors are not made of glass, as most telescope mirrors are. They're fabricated from beryllium. Why did we use beryllium? Well, we're going to operate this telescope at about 40 or 50 Kelvin. And as it slews around the sky, points at different directions around the sky, there are small temperature gradients that will form in the primary mirror. And we didn't want those temperature gradients to spoil the shape of the mirror. So we had to find a material that had a very low coefficient of thermal expansion at this very low operating temperature. And beryllium has that property. The beryllium starts out in a powder form, and then we compress it under tremendous heat and pressure into a billet of material. And then after going through all the trouble to do that, we machine almost all the beryllium away to produce a very lightweight mirror segment. And the figure of merit here is areal density, mass per unit area. And by that metric, the JWST segments are about 6 times lighter than the Hubble Space Telescope mirror, and they represent the current state of art in lightweight mirror segments for spaceflight use. Now, how do we polish telescope mirrors? Well, we rub on them with gritty stuff until they get smooth and shiny enough. Now, that is a room temperature operation. So if we're going to polish the mirrors at room temperature and then use them at -400 Fahrenheit, that means that we have to polish in the wrong shape at room temperature in order to get the right shape at the operating temperature. This is done through the magic of computer modeling, but computer modeling is not perfect. And so we had to follow an iterative process whereby we would polish the mirrors part way and then put them into a specially instrumented space simulation chamber at Marshall Space Flight Center near Huntsville, Alabama, where we could cool them down to the operating temperature and observe them with special optics test equipment to reveal how the polishing is actually tracking to our computer model. And then we would make small corrections to the computer model and iterate this process to finally achieve the result shown here in the upper right. And this is real data. So this is what the figure of a JWST mirror segment looks like at ambient temperature. The colors denote relief. And when you cool the segment down to its operating temperature, you end up with no relief. You end up with just this perfect figure. And so, as you can imagine, this took a long, long time to achieve this, but we did get it done. And this is one of the reasons why it took so long to build the Webb telescope. Now, we did use robotics to assemble the telescope. This is in a clean room at Goddard. And this robotic pick-and-place machine is being used to help populate the telescope structure with the actual flight mirror segments. The mirror segments have covers on them to keep them clean, so that's why they look black. And this robotic arm has a very high precision end effector or tool on the end of it that is helping the technicians get each mirror segment into exactly the right place. You get the idea. All right, now these mirror segments have to be made to play together as one. So each mirror segment is mechanized in 7 degrees of freedom. The 6 that you're familiar with plus radius of curvature. And with those mechanisms, we can adjust the mirrors in tip, in tilt, in piston, and radius of curvature. And we have to do that adjustment to a precision that is a small fraction of the wavelength of light that we're observing. And so when we first deploy the telescope and point it at a star, we have 18 separate telescopes. And then the image from each of those 18 segments has to be identified so that we know which image goes with which segment. And then they have to be superimposed onto each other.
Well, we did the segment identification.
The mirrors have to be
then we formed
brought
the image
into
array.
phase alignment.
And then once they were in the image array, we used this phase retrieval technology to position each of the mirror segments and the secondary mirror itself such that all the optical aberrations were effectively eliminated. We tilt the mirror segments to bring the light from each mirror so that it falls on top of each other at a common point in the middle of the detector. And we call that image stacking. And that concentrates all the light in a single place, but the images, the segments themselves are not cooperating. They're not working together at that point. They're all their own individual telescope. And the next phase in the process is something we call coarse phasing. And that's where we adjust, well, literally it's the piston. It's the up and down motion of the mirror segments relative to each other. We control the piston of the segments so that they all come together in creating a complete monolithic primary mirror.
All right, so that work is behind us now, and this is the resulting essentially perfect image, first image from the JWST. And you know, we're very, very happy with this image. And some of the most impressive things in the image is actually the background. You can see the whole sky filled with galaxies seen in this image. All right, and so this is an actual in-flight picture of the primary mirror taken as part of the segment alignment process. These are the 18 images that are in an arrangement after understanding which segment goes with which image. Then we stack those up as described, and then we do the piston adjustment to bring them all into perfect phase, and that's the result. And in this GIF animation, we're comparing this image from the web to a corresponding image taken with NASA's Spitzer telescope on the same star. And so you can immediately see the high angular resolution that JWST is enabling for the first time in the infrared. So we're pretty happy with these results. The telescope is working exactly as planned. Let's take another look at that giant Sunshield. It is literally the size of a tennis court, 73 by 40 feet. And it has an SPF of more than 1 million. So if you had this on the beach, you would be very well protected. It's made of a heat-resistant plastic-like material called Kapton. Each layer is thinner than a human hair. The sunward-facing layer is coated with silicon, so it actually looks pink in real life. And the remaining layers are coated with aluminum. And the Sunshield has to have a special curved shape in order for it to perform thermally, and in order that stray light reflecting from it not get into the telescope. And those of you who sew may realize that in order to make something curved out of flat cloth, you have to make a quilt with lots of seams. And each layer of this Sunshield is in fact a quilt consisting of 50 pieces and 7,000 inches of seaming. In this case, the seaming isn't done with needle and thread, but with thermal spot welds. And so creating this Sunshield and deploying it was really the highest risk item in the whole Webb mission. And that risk is behind us now, and the Sunshield has performed as expected, and the Webb is reaching its desired temperatures. This is a deployment test of that Sunshield, where we're practicing how to fold it up into the giant pallet structure. These tables on each side are there to provide gravity offloading. They don't exist in space. These telescopic booms are what you saw in the animation. And you can also notice a person appearing in the center here that gives you an idea of how big this Sunshield actually is. And if you look closely, you can see the quilting as well. And so what you see here is exactly what happened in space, sans the people. Okay, and you get the idea here. All right, let's talk a little bit about the science instruments. The telescope, the purpose of the telescope in the system, the function it performs is to collect the light from the objects that we're observing and relays that light into the science instruments, which are located behind the primary mirror. Those science instruments do a little bit of processing on the light to help us extract the physics information that the light contains. And the science instruments also digitizes the light into ones and zeros so that that signal can be transmitted back to the Earth via radio transmission. The Webb has 4 science instruments, 2 of which were led by women. The first is the near-cam instrument shown here. This is the main near-infrared camera on the Webb. It was produced, led by Marcia Ricci of the University of Arizona, and produced with her contractor, Lockheed Martin Advanced Technology Center in Palo Alto, California. This is the instrument that will take the images of those first stars and galaxies to form after the Big Bang. This is the mid-infrared instrument, the instrument that observes farthest into the infrared spectrum. It's both a camera and a spectrometer. It was led by Gillian Wright of the UK Advanced Technology Center in Edinburgh, Scotland, along with a consortium of 10 European countries and NASA's Jet Propulsion Laboratory. It was a very programmatically complex team. However, this instrument was the most problem-free development, and it was the first instrument delivered. This is the main near-infrared spectrometer on the JWST. It was built by the European Advanced Technology Center in Noordwijk, the Netherlands, along with Goddard Space Flight Center. And it's a very unusual type of spectrometer in that it can target 100 sources simultaneously, obtain their spectrum, and keep all those spectra separate. And that was a key development because these primeval galaxies that we want to observe, they're very, very faint. And so if we had to observe them one at a time, we would never get a large enough sample size within the lifetime of the mission. So we have this multi-object capability that allows us to observe them 100 objects at a time. And then the Canadian instrument shown here is really 2 instruments in one. It is a fine guidance sensor that helps us point the telescope at the objects of interest. And the Canadian fine guidance sensor can sense pointing to a millionth of a degree, or about 3 milliarc seconds. And it also contains a science instrument function, which is very much geared toward obtaining spectra of those exoplanet atmospheres that we spoke of. Now, when we finished integrating or attaching the science instrument payload to the telescope, then we put the whole assembly into a specially designed shipping container that maintains it in the ultra clean environment that it needs to remain qualified to fly in space. And we loaded that shipping container into a C5 transport plane. It just barely fits, but we did get it in there. And we flew it from Andrews Air Force Base outside Washington, D.C. to Houston, Texas, to do more testing at the Johnson Space Flight Center. At Johnson, we did something called an end-to-end optical test. We put the observatory into the largest cryogenic space simulation chamber in the world. It's called Chamber A at Johnson, and it was designed and built for NASA's Apollo program. This is a view looking through the door of that chamber, and you can see the Apollo command module in there being tested. We brought this chamber out of mothballs and refurbished it for the JWST program. And we were able to roll the JWST telescope into this chamber, suspend it from the top on rods, and then cool the whole thing down into the environment that it will experience in space. And we were able to use special optics test equipment in the top of the chamber to actually shine light through the whole optical system, and just as it will occur in space, to ensure that everything is working properly. This is a test that we did not do on the Hubble Space Telescope program, with consequences that I suspect many of you are aware of. And so, although this is a very difficult test, we did not skip it on the JWST program. And it's good that we didn't, because we did actually find problems in this test. But of course, all this work is long behind us now. Then when we finished that test, we went back into the plane and we flew from Houston, Texas to Los Angeles, California, where our contractor Northrop Grumman Aerospace Systems in Redondo Beach, California, would then add the spacecraft and the Sunshield to the assembly, to the telescope and its science instruments. So this is in a clean room at Northrop Grumman, and this is showing that integration. This is the Webb telescope with its science instruments in the stowed configuration for launch. And we're integrating it with the Sunshield, which is in this big pallet structure here. And the spacecraft is underneath it, so you can't really see the spacecraft in this animation. And after we integrate these assemblies, of course, we have to test the whole thing to make sure that we integrated it properly. And then we have to put this whole assembly into a vibration test facility to simulate the vibration that it will experience during the rocket flight to space. And then we also had to put it into an acoustic test facility where it is blasted with giant loudspeakers to simulate the acoustic energy that it'll experience in the rocket flight to space. And then we had to put it through an extensive battery of tests to make sure that we really did pass those vibration and acoustic tests. So all that work was completed. But now that we've added the Sunshield and the spacecraft to the assembly, it's too big to fit into the aircraft. And so instead, we put our shipping container onto a roll-on, roll-off transport ship. And we shipped it out of Seal Beach, California, which is just south of Los Angeles. And we went through the Panama Canal to French Guiana. And this is the first time NASA has ever shipped a flight payload by boat, but that all worked well. And this is pictures of encapsulation at Kourou Launch Center in French Guiana. So this is what you see here is the rocket is in a giant vertical assembly building, and there are work platforms set up at various positions along the length of the rocket for people to do work. So this platform is about here, and it's the point where the JWST is attaching to the rocket. And so this is literally the last view of the Webb on Earth. And in this particular rocket, the fairing, or nose cone, if you will, is lowered axially over the payload. So that's this process that's happening now and shown completed here. Okay, and then the Webb was launched on Christmas Day. Let's just take a moment to look at that.
The command will be issued to ignite the solid rocket boosters. The James Webb Space Telescope will be on its way. T-minus 30 seconds and counting. Standing by for terminal count.
À tous de DDO, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff.
Décollage.
Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported.
All right, now we put a camera on the upper stage of the rocket to film the actual separation of the JWST from the launch adapter, as they call it. So this is actual footage from space. So you're seeing the bottom of the spacecraft there. And you will get to see one deployment, the deployment of the solar array, which was the first thing that you saw in the animation video. And then that's the only deployment that we have footage like this of. And there goes the solar array. All right. So this is where we are now. We're coming up on day 80 or so after launch. We were launched on Christmas Day. We are in the process of commissioning the telescope, and that's going great, as you've seen. And when we finish commissioning the telescope, then we will commission all of the science instruments. The science instruments are on now and seem to be working, but we will fully calibrate them and get them ready for science. And then in a June timeframe, you will have the first early release imagery from the Webb. So you should certainly see that in the news. And then a few months after that, there will be early release science results from the Webb. So it's a very exciting time right now, and but everything is working as planned.
This is your telescope, an engineering marvel, an exploration powerhouse. Use it to look back in time and explore the first galaxies that formed after the Big Bang. To peer into atmospheres of planets orbiting the stars. It's your eyepiece to the uncharted, unknown, and unimagined. This is the largest, most complex, and challenging space telescope ever constructed. It will change our understanding of the universe and our place in it. The James Webb Space Telescope. Equipped with the largest primary mirror ever to be flown in space, at 6.5 meters, it's more than 6 times the size of the Hubble Space Telescope primary mirror. Webb's 4 cutting-edge infrared instruments and cameras operate at super cold temperatures. Temperatures colder than the surface of Pluto. Getting this cold is done with the help of the largest Sunshield ever flown, a 5-layer, tennis court-sized sunshield that blocks heat from the sun, Earth, and Moon. Webb will be the first telescope to detect light from the most distant galaxies in the universe. These first galaxies formed about 13.5 billion years ago, only 300 or so million years after the Big Bang. Webb carries advanced technologies to tackle some of the most fundamental questions about the universe. How did the first galaxies form and evolve? Are there chemical signatures of the building blocks of life on other worlds? Is our solar system unique? Launching such a large telescope into space is an incredible engineering challenge. Fully deployed, Webb is too large to fit inside any rocket fairing. Engineers designed it to be folded, like origami, to squeeze inside the European Space Agency's 5-meter diameter Ariane 5 rocket fairing. After launch, controllers on the ground deploy Webb remotely. Deployment is an intricate ballet. For nearly 3 weeks, controllers carefully unfold Webb. After this delicate dance, Webb's golden mirrors are precisely aligned using motors behind each hexagonal mirror segment, adjusting them to form one perfect mirror. Once the instruments are fully cooled, the exploration will begin. Webb is a technological challenge like no other, born of the efforts of thousands of people across the United States, Canada, and Europe. The James Webb Space Telescope is your telescope. Use it to explore, to challenge theories, to see sights yet unseen. It's yours to unfold the beauty and mystery in the universe and our place in it.
All right, that's the hour. I think we can leave it there. Those are my remarks for you today, but you can really follow the action with JWST by going to our website and also our blog site. Every little thing that we achieve in flight is usually accompanied a few days later by a blog post that are written at a popular level. And so that's the Reader's Digest version of the Webb mission, and I'm happy to answer questions for as long as you have them.
Well, thank you very much, Dr. Greenhouse. That was truly remarkable. I really appreciate for you to say it's a Reader's Digest. I mean, I've now know 100% more than I knew. Just the assembly and transport alone, just to get it out into space, really, I imagine there were quite a few sleepless nights and gray hairs involved with that whole deployment process and assembly. I just wanted to clarify something. So on one of you were talking about that the way Webb is going to work will be looking at, especially if we're looking for, say, water on other planets. So is it correct to say then we're using, I guess I'm thinking about this as sort of like a different spectrum. So we're using a different spectrum to subtract out the various spectral patterns so that you can actually see that water signature. Is that?
Yeah, we when we observe these planets, we're necessarily observing the planet plus the star. And so to get the spectrum of the atmosphere, we need these special configurations, like the edge-on configuration, that allows us to separate those two spectra so that we can see just the spectrum of the planet's atmosphere. And that transit spectroscopy technique allows us to do it, at least for the special case where the solar systems, the plane of the solar system is along our line of sight.
Okay, and I have to be honest, I feel a little sheepish even saying this, but I think in my mind, I was thinking the Webb would be traveling a bit, but the Webb actually is stationed at this L2 position. And so and you might have shown this in a slide and I missed it, but what's the distance that we're talking about that the telescope will exist from Earth?
Yeah, this L2 point is 1 million miles from the Earth in
Okay.
the anti-sun direction.
Okay, okay. I see we have quite a few hands up, so I do have a few more questions, but let's go to Bob Verstein.
Matt, a fantastical accomplishment and wonderful presentation. It's nice to have a real project scientist to explain this to us. You tested it under a lot of different conditions. You froze it, you shook it and everything else, but you couldn't test it under zero gravity. There's tension from that and things probably change shape. Did you account for that or did you have to?
Oh yeah, that's part of the whole art and science of building things like this. We have to test in the presence of gravity, but we're operating in an area where there's only microgravity, and so we have to use tricky techniques to do what's called gravity offloading of the structures and so forth that we're testing. And we have to also have special measurement techniques that allow us to take into account gravity. But yeah, that's one of the things that makes it hard. If we could somehow build all this in a weightless environment, it would be so much easier. Yeah.
Richard?
Fantastic show. Very large compliments to your presentation. It was realistic and fantastic. I have a question that may be hard to answer in the sense that we've noticed from the Hubble and other particular technological advances in space that they have an expected life, but with technology moving rapidly, that life estimate is sometimes an error. And so I was just really kind of wondering if there were estimates of longevity for this process.
Okay, so the question is, what about the limited life of the JWST? And at first we were concerned that propellant might limit the life of the Webb. This rocket flight that we got to the L2 point turned out to be so precise that the propellant that we had on board to help us navigate to the L2 point, much of it was not needed. And so now we have so much propellant on board that it would last at least 20 years. So that simply means that propellant won't be the thing that ends the JWST's life. It'll be wear out of something else. And we can't know in advance what that something else is. And so, when we do life testing, the engineering lifetime requirements for the JWST was 5 years. When we do life testing, we typically put a factor of 2 on that. So all of the systems have been tested to have verified capability of at least 10 years. And then beyond that, you're on borrowed time. Now, the Hubble was made to last a very long time due to astronaut servicing. There's no astronaut servicing possible at the L2 point. And so the lifetime of the Webb won't be extended by that sort of servicing as Hubble was. Missions that we develop, to follow the Webb will likely have servicing as a much more prominent part of the mission. But for the Webb at the L2 point, servicing is just not planned for it right now.
Thank you very much.
Hey, John, go ahead.
Okay, thank you for